Hello and welcome back. So, since last time I started looking at how passive components can be modeled, today it's time to look at the capacitor's brother, the inductor. So this component is basically a piece of wire. So how hard can it be to model? Well, to start things off, I prepared this little experiment. So I'll be injecting an AC signal into an inductor, and I've got also a resistor in series. Basically this is an RL, so resistor inductor low pass filter. Let's see what the simulation is telling us about this. Basically it works like a low pass filter, as the name suggests. It has a cutoff frequency, after which the output signal should steadily decrease. Now let's see this thing in action. Let's see how this thing behaves in real life. So what do you think? Will it be just like in the simulation or not? And for that purpose, I got this setup right here. So basically I'll be using a signal generator, amplifying it through the amplifier, and then passing it into this little circuit. So what I got here is a 10 millihenry inductor. So even though it's a very big inductor, it's not that big, so size doesn't always matter. And it's in series with a 200 ohm resistor. And my oscilloscope probes are not that good quality. And my oscilloscopes are probing the signal coming into the circuit and then the signal at the output of the circuit. So basically I'll be measuring the output of the RL filter. So let's start things off. So now, even though it's a very small frequency signal and the filter is not really doing anything, we can already see that the output signal is smaller than the input. So the output is already around 250 millivolts smaller than the input. Let's increase the frequency, see what happens. So I've increased the frequency tenfold. The ratio between the two signals is still roughly the same. So no change, so the filter is not really filtering yet. So now I'm up at 5 kHz. We can definitely see that the blue signal is smaller. And we're already seeing a phase shift, so the filter is starting to come into play, and it's filtering. With higher frequency comes higher attenuation, of course, and at some point you can barely see the output signal. So let me just increase its amplitude a bit. So right now the voltage base for the output signal is 10 times smaller than the one for the input. So we got 20 millivolts per division for the blue signal, 200 millivolts per division for the yellow signal. So we've reached a point at which we can almost no longer see the signal coming out of the filter, so the filter has completely attenuated the input signal, and now the input signal is coming back. So we're at 2 MHz and we can clearly see that the input signal is making a comeback. And again, with increasing frequency comes a higher signal. So just like with the capacitor filter, we can see that the filter starts filtering at some point, and then it stops filtering at another point. So right now if I would increase the frequency even more, then the output signal would be even larger. So let's see what's going on. So what happened here that caused this sort of behavior? So you may have already guessed what the first problem is with the model, and that is the series resistance. The inductor, like any piece of wire, has a bit of resistance. And fortunately, this can usually be found in a datasheet. So this is a generic datasheet for a random inductor, and we can see that one of the parameters which is listed here is this maximum resistance. So it's either defined as Rmax or RDC max or under some various form. And in this particular datasheet, the 10 millihenry inductor has 42 ohms. So if we add this 42 ohms into the model and resimulate, we can see our first effect. And that being that the output signal is never at the level of the input signal. Basically, even though the inductor is not doing anything at very low frequencies, so basically it's just like it's not even there, you already have a voltage divider built with the series resistance and your output resistance. So that's why in our experiment we never got the output signal equal to the input signal. Now the datasheet is giving us another very interesting piece of information. and that is this thing. So what is the resonance frequency of the inductor? Now, the inductor, just like the capacitor, apart from inductance, has also a bit of capacitance. And this is modeled as an equivalent parallel capacitance. Now, the datasheet doesn't directly tell you what the capacitance is, but it tells you that for a 10 millihenry inductor, at least the one in this datasheet, the resonance frequency is at 350 kilohertz. Now, you can work out from the value of the inductance and the value of the resonance frequency what the capacitance is. So what I got here is an inductor that has inductance and a few picofarads of parallel capacitance. And if we check out how this behaves, we see this effect. So it's behaving like an inductor, it's filtering, you got the resonance frequency when the output is almost non-existent, and then you're starting to get the input signal coming back again. And if you put all the things together, so inductance, resistance, and capacitance, you get a behavior similar to what we got in our experiment. So input signal attenuated from the beginning, filtering action, resonance, and then the capacitive action. So these are the three main parasitics that the inductor comes with. Now, of course, LTspice's default model also has this parallel resistance. So we got the series resistance, the inductance, and the parallel capacitance. And the parallel resistance is there to represent the losses that the inductor has. So not all of the energy stored in the inductor will come back out again. And that you can set with this parallel resistance. Now, you may remember from last time, if you go to the Tools menu, Control Panel, and Hacks, you've got two parameters relating to inductors. So we got this parallel resistance, which can either be set to have a certain value or not have any value. And then you need to set if you want your series resistance to be default 0 or default 1 milliohm. So keep in mind to make sure that you set these the right way when you want to simulate inductors. Otherwise, your inductor will have this default 1 milliohm series resistance and who knows what parallel resistance. So let's see some proper models. But before that, I will not be using this sort of setup. So I will not be testing a low pass filter, but rather I'll be measuring the impedance of the inductor. And for that, I'll be using this sort of setup. So the impedance is the ratio between voltage and current. So you can either insert a standard voltage with an AC simulation into an inductor and not plot the current, but 1 over the current. So the voltage being 1 divided by the current, and you get this sort of plot, which of course you can set to logarithmic, and then you will get the value directly in ohms. And if you don't like to work with voltage sources, you can work with current sources and measure directly the voltage. So this will give you exactly the same result, because now you're dividing the variable voltage by the fixed current of 1. So either way will be good to measure the impedance. So let's move on. And this is what a typical SPICE model will look like for an inductor. So what I got here is a power inductor manufactured by Samsung, and we can see the general characteristics of the component, we see its name, and then we see the actual SPICE model. It's quite a complicated model, contains a ton of components, and to use it, I generated an auto-generated symbol, so I didn't really bother with making a nice one, and I got this setup just to measure the impedance. And if we look at it and set a nice scale, so we can see that at low frequencies it does nothing, then it has an inductive behavior, it has a resonance frequency at around 30-40 MHz, and then it starts to have a capacitive behavior. So typical inductor behavior. Now if we compare this to this component's datasheet, which I got right here, then there's not much to compare it with. So the datasheet, for a power inductor at least, doesn't really give you an impedance curve, since you're not really interested in impedance for power inductors. the only thing that would be of any use to compare to our graph is this curve. Basically, it's telling us that the inductor is an inductor up until 20-30 megahertz, after which we have the resonance frequency and then the capacitor behavior kicks in. But other than that, not much useful here. Now, if you want to play around with impedances, then the right component to analyze is something like this. So this is a model which is this time from Murata, and this is not for a power inductor, but rather a ferrite bead. And what makes this special is that this is a component that is especially designed to be used as a filter and to have large impedance. And if we compare the two, so on the left side I got my ferrite bead, on the right side I've got my power inductor, slightly different scales, let me just fix that. So what we can see now, if we compare the two components in roughly the same frequency range, so again we still have the part where the ferrite bead does nothing, but afterwards its response is no longer as sharp as the power inductor. So the thing to remember here is that these two components have completely different functions in an electrical circuit. The power inductor is used to store energy, so it has a very clear inductive behavior with minimal losses, whereas the ferrite is a filter component, and you want this to be as resistive as possible, so the inductance is not as clear. You just have a high impedance as frequency rises. Now, regarding this inductive or capacitive or resistive behavior, we've got another very important piece of information in these two impedance graphs, and that is the phase. So what we can find out is that 0 degrees of phase shift corresponds to resistive behavior. So we can see the power inductor is purely resistive at low frequencies. Then, as frequency increases, we have a plus 90 degrees phase shift, so a purely inductive element. And then, after resonance, a minus 90 degrees phase shift, so purely capacitive. And then at high frequencies, we don't really know what happens. Now, on the other side, on the ferrite bead, same 0 degrees at low frequencies, then we almost hit 90 degrees, and then we drop back down. So we can see that at higher frequencies, the ferrite bead has a clear resistive behavior, or at least it's more resistive than inductive. And that's exactly what you want in a filtering component. And now we can also compare this graph to the one in the datasheet. So this is the datasheet for the ferrite I just simulated. And this time we actually have a proper impedance graph. So I rescaled it a bit, and now we can see that we have a very good correspondence between what's in the datasheet and what's in the simulation. So the simulation is working correctly. So these models are looking quite nice. But is there anything missing? So if we look in the fine print, we can see that we have a defined frequency in which the model is valid, and they're clearly stating that the measurement temperature is a current, 0, makes perfect sense. So this model is valid for 25 degrees and 0 amps of DC bias current. Now, why do you think that is important? Why would they bother mentioning this? Well, if we go back to the power inductor and look in the datasheet in a bit more detail, we can see that we've got a few parameters mentioned here. So we got the inductance, of course, we've got the series resistance, and we got a rated DC current IRMS, which basically means that above this current you will break the inductor, so you will burn out the wire. But you also get a different rated DC current, which stands for ISAT, the saturation current. And these are different values, so they're representing completely different things. And if we look in the datasheet, we have this graph. So this is telling us what's the inductance based on the DC current. And what we'll notice is that the inductance is not constant. So the higher the DC current, the lower the inductance. And this ISAT, so the saturation current, refers to the current at which we are losing too much inductance. Now, do we see this in the model? Well, to find out, I prepared this setup. So I'm no longer performing an AC simulation, but rather a transient simulation in which I'm applying a DC pulse. So I have a plus minus 30 volt square wave, and if I look at the current going through the inductor, we can see that it's a perfect triangle wave, plus 5 amps, minus 10. So it's not centered because the simulation didn't start at 0. I mean, it's quite difficult to get this centered, so you need to simulate for quite a lot of time. But the point is that the current is going in a straight line. And basically, this is according to the general definition of how inductance will give us a certain current after a certain amount of time. So if you apply a voltage to a certain inductance, then this will give you specific current rise in a specific time period. Perfectly nice, perfectly straight. So let's see how this thing looks in real life. So to test this behavior out, I got a similar setup to my first experiment. So basically, I'll be injecting the signal coming from the amplifier through a 1 ohm resistor, on which I'm also measuring the signal level, just to know what's the current going through the circuit, and then I'm passing it through this tiny little 680 microhenry inductor. So let's see what happens when we apply a square wave to this little circuit. So the wave isn't perfectly square, but we can clearly see that the current is rising in an almost perfectly linear fashion through the inductor. So basically this is the inductor in effect. Now let's try to increase the level of the voltage, see if anything changes. So right now the voltage is larger and the current therefore is larger. But still, we've got an almost perfectly straight line showing us that the current is rising linearly through the inductor. So now what I did is I'm applying the same signal amplitude, it's just that it's shifted. So it's no longer a plus minus 4 volt signal applied, but rather it's a plus 8 minus 0 volt signal. And we can see that the current going through the inductor has a different shape. So it starts off going straight, just like before, then it hits this bump, and then it shoots up. So what we're seeing is that the inductor is changing its inductance. So the first slope corresponds to the initial inductance of the inductor of 680 microhenry, and then the second slope, which is much steeper, corresponds to a smaller inductance. So this is basically saturation in effect. After we exceeded a certain current going through the inductor, the core saturates and the current shoots up because it no longer has the same inductance as before. Now it doesn't matter if this is a positive current or negative current, the same effect will still happen. And you can get it only on one side, like here, or you can get it on both positive and negative slopes. So right now I'm giving a peak-to-peak signal of 16 volts, so plus 8 minus 8, and we can see saturation on the positive edge and saturation on the negative edge also. And I think I broke the inductor. So the thing to note about this experiment is that usually the DC current rating and the saturation current for an inductor are usually similar. And if you play around with saturating an inductor, you can end up breaking it, like I just did. So let's see how we can simulate this thing. Now, there are multiple possibilities, and one way is to get a model that actually does support such features. And to that extent, I found this thing. So these are some models made by TDK, and if you go to their website, so I will be leaving links to all of these models that I present down in the description, so go check them out. And what I got here on their website are a bit of data about what they're going to present. So they have simple and precise spice models, so the sort of things that we've seen already. And then they have this thing, the DC superimposition model, which is better because it's super. Now they supply this for 3 types of simulators, so even if you're not using LTspice, you're using one of these other ones, you can still use these models. And now depending on the exact inductor you want to use, you may or may not find the model that you want. So I took one of these models, so the super one for LTspice, and I got it right here. So let's see how this thing behaves. So this is a 470 nanohenry inductor. I'm applying a plus minus 10 volt voltage pulse, and if we look at the current through it, we see this thing. So we no longer have a proper triangle wave, so like the ones we saw before. We have this thing. So we have a certain slope at low currents and then a different slope at high currents, with a clear behavior showing us the saturation. So this inductor saturates at around, I don't know how many amps, and then the inductance becomes much smaller. Now, if we try to see how this was done and look inside the model, we see that, like all good things in life, you don't really know how to get them, because this model is encrypted. I mean, it's very nice that they're letting you use it, but they just won't tell you how it was made. So, what can you do? How could you possibly simulate such a behavior on an inductor that you don't have a model for? Well, fear not, I have some solutions. So, to explain them, first of all, I need to show you another way of expressing inductance in LTspice. So one way is the classical way, in which you have an inductor that has a certain inductance, and just like for the capacitor, where you are able to express the charge of the capacitor, for the inductor you can express the magnetic flux. So you can write its inductance as a formula in the shape of flux equals x times something. So if we run this simulation, both of our models have exactly the same behavior. So the currents are a bit shifted, but exactly the same 2.2 microhenry inductance is visible. Now this is a non-saturating inductor. So how do we make it saturate? Well, the easiest ways I found to do this was using this sort of expression of the flux. So you write a formula in this shape in which you equal the flux to the base inductance times the saturation current, and then you either use the arctangent function or the hyperbolic tangent function, in which you divide the current going through the inductor by the saturation current again. And by using these expressions, you can see that you no longer have a perfectly straight line, but rather you have these arcings. And with the other one, it's roughly the same behavior. So if you use higher currents, then you will see this a bit more clearly. But now you can clearly see how the saturation is being expressed in the simulation. Now there's one more way you can do this, and that is by using the table function. If you don't like all that trigonometry, you can create a simple table in which you define various inductances for various currents. Just don't forget to supply also the negative and the positive currents. So if you only supply the positive currents, then this won't work for negative currents. And now this doesn't work as well as it should, but yeah, maybe you can make this work. It should work, but you can get all sorts of weird behaviors. I personally recommend the trigonometric versions. Now, apart from the two ways of expressing inductance that I showed you, so the classical one, the one with flux, LTspice has another more complex version of expressing inductance, but that's a story for a different time, since that is not really a practical way of expressing inductance for inductors that you buy. That's more useful when you build your inductor. But for now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and hope to see you next time. Bye bye.